And so what I'd like to introduce Jose Maria Martin-Garcia. That's he's actually an excellent scientist, which would be good enough to have him around here. But one of the reasons is also that we co-wrote with Yvonne several of her papers. And so there's a complete list of papers, I think, here. And if you go towards to the end, you can see several papers that I had the privilege and honor to write with Yvonne. And Jose was a very important collaborator on this work. And so he wrote this wonderful program called xAct. That's an add-on to Mathematica, and I think he's going to show you some of the miracles that his software can do. So, Jose.
Thank you. Okay, so it's a great pleasure for me to participate in this workshop in honor of the 100th anniversary of Yvonne. I want to start by thanking the organizers, and in particular Piotr, for letting me speak today. And again, I want to thank Piotr for inviting me to collaborate with him and Yvonne back in 2008 in this great project of studying the Cauchy problem in a characteristic cone. So my role there was to keep track of all these signs and factors that we have in complicated equations. And I did that with xAct. And what I want to do today is to show this project. So the title of the talk is xAct Tensor Computation, 1,000 projects. You will understand in a moment why. And the plan of the talk is the following. I will briefly introduce xAct, explain the status of the project and how to access it, etc. Then I will spend most of the talk showing examples of use so that you get a feeling of what you can do with it and how to use it. And then at the end, I will show just a list of things that are still not there and that people have requested and will be implemented at some point. So let's go first with the introduction to xAct. So this is a project developed since 2002 during my first postdoc in Southampton. And it's all written in Wolfram language, which is very convenient because this is all based in pattern matching, and Wolfram language, the language of Mathematica, is great at it. And it has a little bit of C code for the most demanding parts. xAct is not a package in itself, it's a collection of packages. Currently, there are 24. I wrote the initial ones, but other people are writing now extensions. And there are more under development, and people contact me to tell me in advance, and so I can keep some sort of consistency with them. xAct performs both abstract computations, so in DCL computations, and also component computations, the sort of, I give you a metric, give me the Ricci, give me Riemann, etc. And it can mix them, which is also something that few other systems can. The system has been used already in more than 1,000 projects, and I keep a list here, which from time to time I go to, I don't know, the archives or Google Scholar and see which papers are cited in xAct. So here we have papers on xAct, so papers dedicated to explain the packages. And then here we have per year the papers that cite xAct. It's very small, so you probably cannot read it. Let me see if I can put this bigger. So you can trace the history. So at the beginning, the whole project was inspired by my work with Karsten Gundlach on the non-spherical perturbations of the Choptuk solution, the critical solution of scalar field gravitational collapse. Then we changed to study the formulations of Einstein equations for numerical evolutions, which was a big problem in the early 2000s because the black hole evolution codes were not able to simulate a single orbit. And so we studied with xAct large families of formulations just to see the advantages of each other comparatively. This ended up as suggesting the technique of constraint damping, which was the last ingredient that Franz Pretorius needed to stabilize his code. Then, of course, in 2005, this area disappeared, and we moved on to something else. And I chose to go to second-order perturbation theory. Again, using xAct, and there are some papers here. Then Alfonso Garcia Parrado started using it, Juan Antonio Valiente, some people from astrophysics. And then here in 2009, we have the papers with Yvonne and Piotr, for example, this one. And since then, you see there were like, I don't know, 15 papers per year around 2009 to 2010. By now, there are about 100 papers per year in all sorts of areas. And so these are the last ones. And you see there is a mixture of GRQC, high energy physics theory, also astro-pH, etc. So it's used in various areas of physics and mathematics. There's also mathematics, differential geometry, fluid mechanics, various areas. I think I had the percentages here, more or less, of the areas using xAct. I also want to use the opportunity to put here the list of the authors with more papers citing xAct. Here we have first Mohamed Garoussi, and then following closely, Juan Antonio Valiente, 26 papers, Alfonso Garcia Parrado also. He has helped me a lot shaping the mathematics of xAct. He knows a lot more mathematics than I do. And then we have Luc Blanchet and Guillaume Fay from the Observatoire de Paris. They are the experts in post-Newtonian expansions, which is a really hard area in which they handle expressions with 100,000 terms, each of them very complicated with integrals, etc. They do all of it with xAct now. And myself, Thomas Bagdal, he also knows a lot about xAct. Obina in astrophysics, etc. So yeah, so there are, yes, more than 1,000 different authors in the list of papers. Okay, so if you want to use xAct, the main resource is the web page here. And here you can download the system. You have the collection of packages now available. So there are 4 core packages that I wrote long ago, and then there are many other packages that people are writing. We will see in a moment. So here you have the tarballs, where to download them, and the installation notes. So there is another web page that users of xAct have created to have their own additions and their own examples, so that they don't have to ask me to put it there in my web page. A very important resource for xAct is the xAct forum. It's a Google group. And if we go here, there are, you see, 856 members. We have more than 1,000 threads already. This is a very important source of information about discussions on xAct, on the Wolfram language, on differential geometry, etc. And go back. And then most of the questions are posted there, but some people also prefer to post questions in Mathematical Stack Exchange. So that's another source of, I don't know, for now it's like 200 questions here. Okay, so there are multiple places to access xAct post questions. The structure of xAct, as I said, is currently 24 packages organized hierarchically. That means that when you load a package, it will automatically know the dependencies and load all other packages. There are about 1,500 symbols, which is quite a lot compared to the 6,000 more or less that Wolfram language has. And the main package is xTensor. This is the package responsible for abstract tensor computation. You will see in a moment. And it has like a third of all those symbols. So the core of the system is based on computational group theory. There is a package dedicated just to that, permutational group theory. Then abstract tensor computations, and then component computation. So these packages and some administration stuff. So these are the core packages to do all sorts of computations. And then we have a package for metric perturbation theory. You can do 10th order perturbation theory if you want. Another one for spherical harmonics. around, so all sorts of harmonics, tensor harmonics around spherical space-times in the sphere. So there is a package dedicated to invariants of the Riemann tensor. I will show you some examples here. You can handle products of contracted, I don't know, 7 Riemanns. Spinor calculus, this is something that Alfonso developed. Another package by Thomas on how to handle symmetrized expressions. Package for cosmological perturbations, another one for field theory, exterior calculus, the Newman, MP and GHP form of spinor equations, and other things here. A recent one, a few months ago, is a package for Brouwer algebra. So to handle their representations of the orthogonal group. This is great to handle tensors with symmetries and also their traceless parts. There are a couple of packages to input tensors, that's xprint, and to output in tech, huge expressions, xAct. This is something that Thomas and Barry Waldrop wrote. And then there is an exceptional package written long ago by Hugo Wolkist, and he passed away, and his collaborator, Frank Stabrook, sent it to me. So I'm now the keeper of this package. Okay, so that's the very quick introduction to the system and the status of the system. So now let's go and see some examples of how to use it. So the most important thing to distinguish is these 2 types of computations: abstract computations, indicial computations, and component computations. So let's have a look at the first one. So the first thing we do once you have downloaded xAct is to load the package. It emits some copyright messages. And then we start defining things. This is very alien to mathematics and the Wolfram language, defining things. But it's very useful for tensors because you can prepare some objects and then use them again and again and again without having to specify their properties all the time. So the first thing we do is to define a manifold. It's going to be called capital M of dimension 4. And these are going to be the indices that are used for the tensors living in the tangent manifold. For example, the delta is always defined, right? So we will have something like that. So now we define a vector field, right? And notice that this is a covariant index, this is a contravariant index, and they have to be indices that you have placed here. The system will be able to generate more indices, but when you input indices, you have to use the indices that you put here. This is a contravariant vector field, right? So it's typeset like that. Now we define a tensor, which is twice covariant on the manifold M, and it's antisymmetric in the indices minus A and minus B. Now it's typeset like that. Okay, now we defined a metric. You can work in xAct without a metric, but you can do more things if you have a metric, of course. So the metric is going to have signature of sign -1. It's going to be called G. And the Levi-Civita connection of the metric is going to be CD. So automatically with the metric, many things are defined. The volume form, something that is used with spinors, the Levi-Civita connection, of course, the torsion tensor, which is vanishing, the Christoffel, the Riemann, Ricci, which is scalar, multiple things, the Kretschmann, multiple things. Okay. So for example, if you write this product, the system knows automatically it has to contract the A indices, right? That's true. Now, for example, imagine that you have that product, the tensor F minus B minus C and VC. You can take a covariant derivative with that, so that's just using the Leibniz rule. Again, if you had a... Exactly. Minus is covariant, yeah. And the system automatically detects those contractions. You don't have to... These are abstract indices. Now, we have this covariant derivative. And so we apply the Leibniz rule. And now, for example, we multiply by V, B. And of course, now, because this object is antisymmetric, and these 2 indices are symmetric, we call 2 canonical. This is the fundamental function in the system, and it knows what is 0. Right? So if anything is 0 by symmetry, this function will catch it. And so this is This is the key function in the whole system. So this works by using computational group theory inside. So the idea is that a tensor is like a permutation. You have two sets of symmetries, the symmetries of the slots and the symmetries of the indices. So you put the two groups, one in front, one behind. You have a double coset, and the problem of canonicalization becomes a problem of finding a representative of that double coset, a uniquely defined representative of the double coset. There are very efficient techniques of computational group theory to do this, called things like strong generating sets, Schreier vectors, etc. And so that's how this can be done fast. You can handle, I don't know, tensor products involving 100 indices or so in less than a second. And of course, you can have 100,000 terms of objects, each one having 100 indices, right? So then you use parallelism, etc. It's all fast. So xAct is constructed following Walt's book, General Relativity. This follows strictly all the conventions, etc. But if you want to change them, there are some variables that have by default value 1. This is Walt's conventions. You can change them at the beginning of the session. Don't change it during a session because the system will get confused. And yeah, and you can follow other convention systems. So for spinors, we follow Penrose and Ridley. Okay, so what do I mean by component computations? So we now load the Xcova package, and we have to define a frame. It's going to be called B, capital B, on the tangent of the manifold M, and it's going to have 4 vectors numbered from 0 to 3. Now, what we do is that, for example, we can construct with a C tensor, a component tensor. We just give the array of components. This means a matrix. You can nest more and more lists, and then you can have deeper objects, or objects with more indices. And these are the bases, again, covariant or contravariant. So for example, here we're going to have a vector, right? And a matrix. And notice that I don't follow, to avoid the confusion of whether this is a vector or an n by 1 matrix, I always close the matrices on below and above, right? And I will use colors to distinguish bases. You can use many bases at the same time, coordinated, non-coordinated. Each one will have a color, and then it's very easy to see which objects are basis dependent. When an object is abstract, independent of basis, it's black. When an object depends on a basis, it will have somewhere that color of that basis. Yeah. So I say A is a C tensor. So instead of having a tensor A, as I had before, A of ij, I say A equals this object. And this object is just a matrix, a tensor of rank 2, whose components in the basis minus B, the covariant basis B, the covariant basis B, are these numbers. These could be functions of coordinates, right? But for this example, they are numbers. And again, you can have 4 bases. For example, for Riemann, you would have to have 4 bases because it has 4 indices. And you would have to have nested 4 levels of lists. There are easier ways of these are the indices. Once I give the indices, so this is the object without the indices. And now I give the indices, you see, and now I'm going to use these indices as handles to contract it, to permute it, etc. So imagine that this red thing is just the name of the tensor. Instead of having a capital T, I have that thing, so I know what capital T is. It's the tensor formed by this. Perhaps it's easier if I expand it like this. And I have this vector, right? These are the, because they are the vectors of the red bases, they are color red. So for example, I can now take these 2 objects and contract them, right? I'm contracting the the index B with the index P. So the standard matrix multiplication can be done now with indices, right? This is what we always do in relativity. So I could be contracting the other index, right? Like this could be minus B minus A. And then it would be a different object, but it's still a vector. covector actually. So yes, so if I now contract again, this is 0 because this matrix was antisymmetric. Okay, so again, in here you can use as many bases as you want, change them, all the Jacobians, everything is automatically taken into account. Sorry, I'm going very slowly. So we can do computations together. You see, this was an abstract tensor. This is a component tensor. Canonical still knows how to handle it. And for example, G was the metric, right? So you can, at any point in which you have an abstract computation, you can say replace the metric G by an explicit matrix. This would be Minkowski, right? So diagonal metrics, these are the bases. Okay, so these are like super trivial computations. You can, at any point, you can also remove the objects. This is what is done here. Okay, so let's do something not so trivial. Again, we define a manifold. Now I'm going to define a metric called met, which is going to be printed as G. Right? I don't want to call it G because G is an index now. You cannot have two objects with the same name. G either is an index or a metric or a connection, whatever, but it cannot be two things. So the metric is called met, it's printed as G, right? So internally it's still met. That's the inverse of the metric, and the metric with staggered indices automatically converts to delta. Of course, this is the Levi-Civita connection, so it knows that the derivative of this metric is 0. Now this is the Riemann. Notice the last index is up, that's Walt's convention. That's the Ricci scalar. And this is the derivative I define, right? You can have many connections at the same time in the system. Each one will have its own Ricci. So connections of Riemann gives Ricci, connections of Ricci give Ricci scalar. For example, that's an expression with two Riemanns. I do to canonical, and it knows that it's 0 by symmetry. And again, you can have much more complicated expressions, and it will know that this is 0. So you can have the Riemann and then convert it into Christoffels. Now, dummy indices have that weird form. But then you write this is some sort of magical incantation, and from now on, you will not see them. So this is always needed, but I don't do it automatically so that people are aware that this is happening inside. Because internally, I'm still using these weird indices. The important thing here is that every time that you evaluate something like that, the indices will be different. Sorry, here. Okay, so this is changing number all the time. That's why there are no index collisions for dummy indices. Each time they are different. So for example, let's do something bigger. So that's a Riemann converted to Christoffel, and now convert the Christoffels into gradients of the metric. Now you have that expression. Easy to understand. So now let's do the first Bianchi identity. We have those three Riemanns. We convert them into derivatives of the metric, and now we call to canonical at 0. Right? That did the computation in real time. So let's do the second Bianchi identity. So we antisymmetrize that expression. Now again, we call covariant derivative to Christoffel, Riemanns to Christoffels. That starts growing. Christoffel to grad metric. So now Mathematica refuses to show it all. Well, we can click here and it would show a gigantic thing, but it doesn't matter. Now we call to canonical, and it takes a bit more because this expression is large, but eventually it will realize this is it. And so this is just brute force, but this is how you use xAct. You don't care about more sophisticated ideas. You just do the expansion and let the computer do the whole thing. Okay, we undefine the metric, and here I have a list of other things you can do with xTensor. You can use torsion, you can work with different metrics at the same time, conformal metrics, induced metrics on a given surface. product metrics, so you have like product spaces, and so it's diagonal by blocks. You can use many other tensors, like bi-tensor, Lie derivatives, variational derivatives. You can use other products, like, I don't know, Lie brackets, things like that, or the antisymmetric product of differential forms. You can use inner bundles. This is important for particle physics, and complex bundles, lots of things. It's all documented. There's a big notebook with all the documentation. Okay, should go fast. Let's do something more with component computation. So we define a chart. The chart is going to be called like this. It's a chart on the manifold M. Again, we have to number the basis vectors, which are going to be coordinated vectors now, and we name the 4 scalar fields. That's typical Schwarzschild thing. Now we are going to say that basis and chart are brown. Everything related to those things will be brown. And there are various ways of typesetting the vector fields. So we are going to be using these notations. There are others. Okay. Now, everything in xAct has to be declared, even constants, because we need to know the tensorial character of everything. So that's the C tensor of the metric of Schwarzschild, right? And notice how it says minus, right? Because it's a 2 covariant object. The 0 means it's not a density. These can also handle densities in any combination of bases. So that's the metric now with indices. As usual, we can expand it into bases, right? So, and now notice that we don't get the E with zeros and ones as before, because I instructed that I want the vector typeset as differentials and partials. Okay, let me do this. So I'm going to create a vector. Right? This is just some random vector field. And for example, if I try to lower the index, it complains. That's because I don't have a metric yet defined in the system. I can do the computation manually, but I mean, we created this object met, right? But we didn't tell that met is the metric. I just called it met. How do we tell the system that this is a metric? We do set symmetric. Now we say this is going to be a metric. We are going to be using that chart as the chart of the fields of the component fields inside the metric, and it has this signature. In principle, it should be able. So I did it twice. So it should be able to compute the signature, but just in case it has problems with the signs, it's better to tell how many of positive signs, negative signs, and zeros. Okay, so now it knows the metric, so it can automatically raise and lower indices of everything. This is a contraction. That's a contraction of those 2 vectors. Of course, the staggered metric will be the identity. And now we can just compute the inverse metric by raising the indices. This is the determinant of the metric, and notice that the determinant of the metric is a density. It's a density of weight plus 2. And I'm using Aztec notation. So I just put a number of tildes equals to the weight. And the weights are colored. The weights depend on the basis you chose to define them. So the weights are colored. You can have an object with bases of different colors. For example, a Jacobian, right? A Jacobian has 2 bases. So it has to be a weight plus 1 in one basis minus 1 in the other basis. And that's stored like that. You see, it's a scalar, so it has no bases, but it has now a weight. That's a volume form. And you can, for example, compute one of the entries of the volume form. The volume form has 4 indices, right? Here in xAct, everything has indices. For example, that's our metric. We compute the covariant derivative, the Levi-Civita. This means it's constructed from the partial derivative of the components of the scalar fields of the chart SCHW. This is the Christoffel, and this is the metric. So now we can compute covariant derivatives exactly as we did with the abstract computation. For example, this will be 0 again. That's the Christoffel. Christoffels in xAct are tensors. They are differences of two connections, right? So this thing of Christoffels are not tensors is not right in xAct. Everything has a well-defined transformational, if you want to call it, character in xAct, so that you can compute Lie derivatives of anything, of a Jacobian or anything. That's the Christoffel expanded in components. Very quickly, you can do Riemanns, that's Riemann. Okay. That will be Ricci, 0. That's a Riemann, right? This is like Mathematica. You have boxes of boxes, matrices of matrices. That's the notation in Mathematica for a rank 4 object. Now I'm going to do this super fast, which is Kerr-Newman in Boyer-Linkwitz coordinates. I will evaluate the whole thing. So this is just specifying the metric, define the 3 constants of the parameters. That's the metric. That's the C-tensor. There is this thing that computes absolutely everything. Everything you want to know, including, I don't know, derivatives of Riemann, is computed here. I parallelized it so that I can use my 10 cores in this computer. It takes 8 seconds to compute everything in pretty simplified form. That's the Riemann. So here that has all the components. You can extract individual components. That's the Kretschmann, for example. Or this is how you extract a component. This is the component 0,3 in this basis. Now, imagine that we do the same computation, but in the rotating frame. Again, I'm going to evaluate this quickly. Now we have this change, which is a change of bases. And of course, because it's changing between 2 bases, it has 2 colors of the 2 indices. That's the color of the first index. That's the color of the second index. Now, if we take this object, which was a red metric, and I change it, just multiplying the index minus AC, C minus B, D, T, now I convert it into a blue object. It's the same metric, just in a different basis. So now we can compute, now you see, instead of 8 seconds, it takes 1 second, because we are doing this in a diagonal situation. The reach is still diagonal. That's the Kretschmann, which is even more simplified than before, but it's the same expression. You can subtract this and the other one, and it's the same expression. Okay. I clean up everything, continue. So let's do perturbation theory. So I load the package for perturbations, and I create a manifold, the metric as before, and now I define a metric perturbation. This means H is the perturbation of G with parameter epsilon. So for example, if I perturb the metric G to 3rd order, I get that. The background metric, the 1st order perturbation, the 2nd order perturbation, the 3rd order perturbation, etc. Again, this can be done to any order. Okay, this is just to add colors, because it's easy to confuse indices with perturbation orders. For example, what's the perturbed metric to 3rd order? That will be that expression. Or we can perturb the metric to 2nd order only. That will be this expression here. For example, we can perturb the metric to 3rd order and the inverse metric to 3rd order. If I multiply those 2 things, this is Wolfram language notation for the previous expression and the previous expression. So we get that multiplication. If I contract all metric factors and canonicalize, always canonicalize, and collect factors of epsilon, we get that the product was exact to 3rd order, right? All the corrections are 4th, 5th, and 6th order. Okay, so that was for the metric. Let's do just one computation for a curvature tensor. So I'm going to perturb Riemann. That's the standard formula that you see in all books to first order. I sort the covariant derivatives, so Riemanns appear, but this formula is typically given in a flat space-time, right? That's the typical formula. Now, of course, what happens if I want to do it to fourth order? Well, here it's absolutely the same work. Just that it takes a bit more. That's the formula. For example, we know that here we must have the same four terms hidden somewhere. There they are. The term number 56 is the same structure of the linear terms, right? The other one, the other one, the other one. I use colors a lot to look for things. Okay, that was an example. So variational derivative. We saw this morning the importance of computing variational derivatives from Lagrangians. So there is a package contributed by Teake and Utma called extras, and it's very good at doing variational derivatives. For example, take the variation of the Ricci scalar with respect to the metric. That thing that we can discover is the Einstein tensor. Right? Now, take the Ricci contracted with Ricci, that thing. Well, we do exactly the same thing. And that's the expression now. And again, we contract metric factors, you see. Metric factors are never contracted automatically. Deltas are contracted automatically, but never metric factors. So you have full control on the character of the indices. And we call two canonical. So the magic always happens at this step. So that's the expression. You can do Riemann squared. And again, contract metric factors, canonicalize. That's the expression. This has been used a lot. People studying f of r theories. We put this lots of scalars here, and they just compute equations of motion with this. Okay, and the last example I want to show is how to manipulate scalar invariants of Riemann. So the problem is the following. This is a beautiful story. So we know that Riemann in 4D has 20 independent components. 6 of them are Lorentz rotations. So there are actually 14 scalars inside. Can we express any other scalars? Once we have a basis of 14, can we express any other scalar in terms of this 14? As far as I know, the first one, the first basis given was by Narlikar and Karmarkar in 1948. And it has this, R is Ricci here, and W is Weil. So it goes to degree 7. You need to have 4 Riccis and 3 Weils to have a complete set of information for these 14 scalars. Now, unfortunately, all other scalars, many other scalars might be non-polynomial because this is all based on algebraic things. So lots of square roots, etc. That's bad. So is there a basis such that any other scalar is a polynomial in the basis? Well, there is such a thing, and it involves 38 invariants, and you have to go up to degree 11 Riemanns. So the question is, if you have those 13 objects, how do you construct any scalar Riemann in terms of those 13 objects? But in xAct, again, using brute force, I computed all relations for the first 27 invariants up to degree 7. So if you have products, contracted products of 7 Riemanns, I can construct any relation involving them. I can express any one in a unique form in terms of the basis by Snellen. It would be possible to go beyond with just more computing power. I think it took like a few hours in a supercomputer to find this 27. Now, can we do it with derivatives too? So now here the important thing is the number of derivatives of the metric. And I have computed this up to 12 derivatives of the metric. That means I can have 6 Riemanns or 10 derivatives of a single Riemann, or mixed things. I have all relations among all possible objects computed in this way. And it's this number of relations. So I have a database You put any scalar of Riemanns involving up to 10 derivatives, and I give you a unique form for it. In particular, if that thing is zero, I will find it. Let's look at an example. I'm going to start all over again from the beginning. The package is called inverse, so I create the manifold, the metric. I'm going to print Riemanns as R. And I'm going to create a random Riemann monomial. This red bracket just means scalar. Don't worry about that. So there's a function Riemann simplify that will read the table of relations, and it will find a unique canonical form for all these monomials. Right? So this means zero derivative, zero derivative. So this is a very trivial case. So let's do two Riemanns, each one differentiated once. Okay, so let's see if we find some interesting case. Purely random. Okay, so you see, the expression doesn't have to be smaller, but it will be unique. And these objects that appear in the result are objects in a basis of a smaller number of objects. So this is one of the largest cases. So for example, that's a Riemann differentiated 3 times, a Riemann differentiated twice, a Riemann differentiated once. So we simplify it, and this is going to be something larger. It has to read lots of cases in the database of relations, and that's a unique form of that object. So if you find yourself with one of these linear combinations of scalars of Riemann, pass it through Riemann simplify, and if it's 0, you will find it. Okay, so xAct does many things. We saw all the packages that it already has, but there are many other things that it doesn't do yet. For example, it's not very good at metrics specified by blocks. If the blocks are diagonal, it can handle it. But if there are non-diagonal blocks, it cannot handle it yet in general. Multi-term symmetries. So if you specify objects with Bianchi types or cyclic type symmetries, it cannot handle the general terms, the general case. For this, it needs the theory of John tableaus, not computational group theory. So it needs the algebra of the group of permutations. That's not implemented yet. So Alfonso is working on collecting a collection of metrics and functionality to classify them. But that's not there yet. xAct at the moment, it only does local things. It's all differentiation. There's nothing global. So when I say the def manifold, that's actually just a coordinate patch. Tensors defined along submanifolds like curves, that's not handled yet. Index-free notation. So I noticed that you all use index-free notations now, but xAct is purely indicial. So it would be good to also have index-free notations. And Alfonso has started using it in the exterior package. Perturbations of tensors by components, that's not done yet. It's only perturbations of abstract tensors. And I would like also to support the numerical community. I mean, I come from numerical relativity, so I would like to be able to go from these equations into numerical code. And I know there are several things that need improvement. In particular, Ben Niehoff has already faster methods than what I have here. I should implement those too. So I conclude with this list of the summary. You can read it, but essentially, xAct is a collection of 24 packages. More are being developed. Already 1,000 references are using it. And I would like to mention that in the recent tensor computer algebra review by Malcolm McCallum, xAct was one of the systems that he recommended, particularly the one he recommended for Wolfram, for mathematics. So here there are some recommendations on how to start with xAct. And if you try it, please use the forum or ask me. Thank you.